So, good morning. I hope all of you had a very good Durga Puja holidays. So, let's start with the FIR filter designing. So, we will be basically continuing from where we left in our last class, Puja holidays. Okay. So, today we will start with the designing methods. So, usually there are four types of designing methods, as you can see in the slide. The first one is the Fourier series method without using window. Second is the Fourier series method using window. Then Fourier transform method without using window. Then Fourier transform method using a window. Okay. क्या हुआ ये? One second. Okay. ठीक है ठीक है ठीक है सर, complete है. Yeah. So all these methods they will be covered from the book Digital Signal Processing by B.S. Nair. Okay. So we have already discussed about the frequency responses of the digital filter. Okay. So if you talk about an analog filter, we will be having a low pass filter, this frequency characteristics just like this. So 0 to omega c, there will be a pass band, and then it will be in the there will be what you call no signal component will be passed in the stop band. Okay. In the digital domain, what happens is that if you consider that the frequency components they will be varying in the region of 0 to 2 pi, which we have already discussed why 0 to 2 pi, then you will be seeing that 0 to omega c you will be having the pass band, and then omega c to pi it will be stop band, and then the frequency characteristics they repeat itself in the pi to 2 pi region. So herein you see the mirror effect. So pi to 2 pi minus omega it will be again stop band, and 2 pi minus omega to 2 pi it will be a pass band frequency characteristic that would be obtained. However, if we convert this into the frequency region of minus pi to pi, then we will get minus pi to minus omega c, we will be having the stop band, then minus omega c to omega c we are having the pass band, and then omega c to pi we will be again be having the stop band. Okay. So usually when we do the numericals, the frequency components varying in the region of minus pi to pi, it becomes quite easier to work with. So we will be looking into the second type, the representation of the frequency characteristics of the digital filters uh, within this frequency range minus pi to pi. Okay. Similarly, if you look into the high pass filter, in the high pass filter, what you will be having, the frequency components in the digital filter it would be minus pi to minus omega c, and then minus omega c to omega c we will be having the stop band, and then omega c to pi we will be having the pass band again. Okay. Then similarly in the band reject filter we will be having this kind of characteristics, and in the band pass filter we will be having this kind of characteristics. Now understanding these frequency characteristics is very important when we go for filter designing. So you please keep this in mind. Okay. Now starting with the Fourier series method without using window. So initially we will start with the low pass filter because it will allow us to understand how we are designing the FIR filters, and then from there the same logic will be applied to the other types of filters also. Okay. So the first step in this method is the draw the frequency response. Okay, so we are talking about the low pass filter, right? So just now what we have seen that a low pass filter frequency characteristics of a low pass digital filter, it would be given by minus omega c to omega, and somewhere we will be having minus pi to pi. This would be our frequency characteristics, and we will be having the modulus of A, or in some books you will find modulus of M, whatever you ask. So basically that is the amplitude. Okay. So what we are having? We are having a pass band in the region of minus omega c to omega. That is the important thing. So first we have to draw the frequency response of the filter, what type of filter we are trying to design. So herein we are trying to design a low pass filter. So this is the frequency response of the low pass filter, and we can see over here that we are having a pass band in the region of minus of omega c to omega c. Okay. Then our next step is to calculate the impulse response. Why we want to do carry out the find out the impulse response values? The reason being, what is impulse response? Impulse response is nothing. When you give an impulse input to a system, we get a series of outputs. Now this series of outputs, they are related to the transfer function of the system. Now from this Hn, which is the output, or the we can say the impulse response, when we have given an impulse input, it can be converted into the transfer function of the system, and these are helpful in calculating Yn, output of the system, when we give which is basically the Yn, when we give an input of x of n. Am I clear? Because what we have discussed y of n is given by x of n convolution of h of n. Okay, so this convolution, it is in the time domain, and if you talk about in the frequency domain, what we discussed? We discussed that y of z, it would be equal to x of z multiplied by h of z. What is h of z? H of z is nothing but the transfer function of the system, right? So how we get from hn to hz? Hn to hz, we can get it by applying the z transform on hn. Am I correct? Am I understandable? Any doubt? No. Okay. So the thing arises, the question is how we find out these hn values. Now these hn values can be easily found out using this equation, where the hn is given by, hn is equal to 1 by 2 pi integral of minus omega c to omega c. See this passband limit, minus omega c to omega c, h of omega multiplied by e to the power j omega n d omega, and if you simplify it, it is something like that. So why h of omega is missing from here? Because in our last class we have discussed that h of omega, we usually considered it as 1 for the sake of our convenience. Okay, so from here if you see the n is varying, so we can get vary the values of this n and we can get the hn. Okay, so hn, it usually varies from h of 0 to h of capital N, where capital N is nothing but the order of the filter. Okay, so what is the order of the filter? Order of the filter is basically given by the highest power of the polynomial in the denominator. Okay, in the denominator. Why in the denominator? Because we have previously the general what you call, the statement is the highest power of the polynomial either of the numerator or the denominator. Okay, but the thing is that we have a clause, we have discussed about the clause, that the number of poles should be greater than equal to the number of zeros. So just by looking into the number of the order of the polynomial in the denominator, we can directly say what is the order of the filter. Okay. Again, in our last class, we have also, just for your recap, we have discussed that length of the filter, it is nothing but capital L is equal to capital N plus 1. Okay. Now, let's look into the next step. The next step is calculate Z transform of H of N to get the transfer function. And then we go for the realization of the filter. Okay. Then we go for the realization of the filter. So this is the generalized step for designing a low pass filter. Okay. So how we are getting this equation from the frequency characteristics, it is important. As I told you, in all the other filters, this component under this integral, it will only change because the passband region, it will change. Okay. So let's look into one of the examples. So the first example is design an ideal low pass filter with a frequency response given by capital HD e to the power j omega, where D stands for desired frequency response, which is given by 1 for modulus of omega varying from 0 to pi by 2 and 0 otherwise. So what it is given, omega, modulus of omega, it is varying from 0 to pi by 2. That means omega would vary from minus pi by 2 to pi by 2. Simple. So the second thing was HDN, it would be equal to 1 by 2 pi minus pi by 2 to pi by 2 e to the power j omega and d omega. Then you just simplify it. So 2 pi it comes, when you integrate it, you get e to the power j omega and it will come over here, and the uh, operator over here is omega. So you get this extra term jnn, which comes as 1 by jnn, jn. Okay, 1 by jn multiplied by e to the power j omega n within the limit minus pi by 2 to pi by 2. This is all class 11 12 basics integration, right? Now from here what you take, you do take 2 and j and take it within the bracket, and pi n n 1 by pi n, it remains outside. And then when you open up to this thing, you open this limit, so you get e to the power j pi by 2 n minus of e to the power minus j pi by 2 n. Okay. Now I think you do remember that there was a trigonometric equation where we had e to the power j theta minus of e to the power minus j theta, it is equal to 2 of j sine theta. Okay. So if we take this 2 of j over here, we get sine of pi by 2 n, it is the theta. So sine of pi by 2 n divided by pi n. Okay. So this component, it became the sine theta basically, right? Now next, find the values of hn for l equals to 11. Okay, then find hz. So when l is equal to 11, we have capital N equals to 10, right? So hdn over here, it will vary from sine of pi by 2 n divided by pi n for n less than equal to 5. That is, here we have a generalized formula of n by 2. Okay, and 0 otherwise. So what we get for n equals to 0, we get hdn limit of n tending to 0 sine of pi by 2 n by pi n. Why have we have used this while our equation is only this one? This is because when you put the value of 0, n equals to 0, what will happen? 0 by 0, it will become indefinite in number. To avoid that condition, for n equals to 0, we have used this limit, okay, so that we can apply the L Hospital's rule over here, which says limit of theta tending to 0 sin theta by theta is equal to 1. So here, and if you see, we get sine of pi by 2n divided by pi n. Okay, now this is not in the form of sin theta by theta, so what we have to do, we have to divide it by 2 and multiply it by 2, right? So this part 1 by 2, it comes out, and this rest of the part, it becomes in the form of sin theta by theta, right? So this becomes 1 and we get hd0 equals to half. Okay, now similarly, what you have to do, you have to find out the other values. N equals to 1, 2, 3, 4, 5. Just put the values of n and you will be getting the other values. Now we have already discussed that for the FIR filters, what happens? HD1, it is equal to HD of minus 1. HD2, it is equal to HD of minus 2. HD3, it is equal to HD of minus 3. HD4 equals to HD of minus 4, and so on. Okay. Now the next thing is, once you have got the HN values, we have got when n is varying from minus 5 to 5. But in our Z transform classes, we have talked that we want an unilateral Z transform for the filters, right? Why that is so? That is so because if you talk about this Z transform, if you get say some values x of say minus 5 multiplied by x of minus 5, so this term, it becomes x to the power 5. So are there any operator to implement that? There are no operator to implement this one. Okay, so to avoid this condition and to make the filters reliable, we have to convert these HN values where n will be varying from 0 to 10, or if you want to generalize, 0 to capital N. Are you getting my point? So for doing that, we use this equation h of z, it is equals to z to the power minus L minus 1 by 2 multiplied by summation of n equals to 1 to L minus 1 by 2 h of n multiplied by h of n plus of h to the power n plus of z to the power n plus z to the power minus n, and then plus of h0. So this portion hn multiplied by z to the power n plus z to the power minus n, it is within this summation limit. Okay, this h0, it is an independent factor. So over here, if you see, L minus 1 is 10 by 2, so z to the power minus 5, then h0, it comes here, summation of n equals to 1 to 5 and the rest values. So what it does is that it allows you to generate the transfer function where you have all the z operators in the form of z to the power minus n. Okay, so we have a delay z to the power minus 1 which can help us in implementing z to the power minus n components, right? So in this way, you have to find out the transfer function of any given system. Now similarly, if you look the second example where we have given design an ideal high pass filter. Here what is given? 1 in the when the omega modulus of omega, it is having a value of pi by 4 to pi. So first thing what we have to do, we have to draw the frequency response minus pi to minus pi by 4 and then pi by 4 to pi. So now we have got the limits. Now if you say there are two pass bands, so we have got two integrals. Just solve it. Okay, just we need to solve it, right? Same thing, same again for n equals to 0, limit n tending to 0, because in both numerator and denominator you will be having the n values. So just do it, so you will get the values. Similarly for over here you can calculate the hn for n values of n equals to 1 to 5. Okay, and then you can find out the transfer function of the system. Similarly, if you look into the ideal bandpass filter, so it says pi by 4 to 3 pi by 4. So minus 3 pi by 4 to minus pi by 4, then pi by 4 to 3 pi by 4. Again, you see the limits, integrals are there. Then you do the what do you call, you perform the integration and you find out the equation, and from that equation you find out the Hn values. Okay. Now let us say while discussing about the uh, what do you call this frequency response by this distance method, we were discussing how we can calculate it from the transfer function itself, because ultimately that is leading to the transfer function. Now how we can do it? So let's see over here. Suppose we take up this example, h of z is equal to 0.5 z to the power minus 5 minus of 0.32 within bracket z to the power minus 3 plus z to the power minus 7. Okay, so I have taken this equation, but it can be applicable to any of the transfer functions. Okay, for the sake of simplicity I have taken this one. Now if you see, when we are talking about the amplitude and the phase response of a filter, where we are interested at the point e to the power j omega. Okay, so this z, it will be replaced with e to the power j omega. So 0.5 e to the power minus j 5 omega, because 5 is already there, that's why. Similarly you change each of the z values with e to the power j omega, and you get this kind of equation. Okay, 0.5 e to the power minus j omega 5 minus 0.32 e to the power minus j omega 3 minus 0.32 e to the power minus j omega 7. Okay, now we know that e to the power j omega, it is given by cos omega plus j sin omega, but over here we are having e to the power minus j omega something, so it will be cos omega minus of j sin omega and whatever the value we are having. So see, this one, it comes out to be 0.5 cos of 5 omega minus j sin of 5 omega. The second factor, it comes out like this, and the third factor, it comes out like this. Okay, now what you have to do, you have a real number and you have a complex number in each of these cases. So you have to simplify it so that you can segregate all the real and the complex number or the imaginary numbers. Okay. Now it is in the form of A and B. Okay. So A plus JB basically. So modulus of H omega, it will be given by A square plus B square, and phase of H omega, it would be given by tan inverse of B by A. Okay. Now at different frequencies we had discussed 0, pi by 4, pi by 2, 3 pi by 4, and pi we had discussed. Now you put this value in these equations for omega equal to 0. You calculate all the values. Then from there you can calculate modulus of H omega and phase of omega H omega, right? Similarly, you put the value of pi by 4, you perform this. Okay. So in this way, what you can do after calculating everything, you can find out the response in this format: omega 0, pi by 4, pi by 2, 3 pi by 4 pi, amplitude are these values, and then phase values you can calculate. Okay. Now another type of example what you will be getting over here is that you can get in this fashion. Okay, cutoff frequency equal to 500 hertz, sampling frequency equals to 2000 hertz, order of the filter is 10, length of the filter is 11. Now we have learned in a different way. So over here what we have to do, we have to calculate omega c, which is equal to 2 pi fc by fs. Okay. Now fc is 500 hertz and fs is 2000, so it comes out to be pi by 2. So from here then you have to find out the transfer function values. Okay. So once you find out that thing, from there you have to calculate the other the parameters and the transfer function. Okay. So basically if you see, after this point we have to go back to this equation. Basically we have talked about this one only, right? So this is the thing. So you please try to do this numerical on your own while I am here. Okay.